In the previous Thermochem video, we looked at temperature changes. This one, we're going to look at phase changes. We might remember the heating curve. When we're talking about temperature changes, we're looking at those line segments with positive slopes, so the A, B, C, D, E, F. When we're looking at phase changes, we're looking at those parts of the curve with zero slope, so DE represents the conversion between liquid and vapor, and the BC line represents the conversion between solid and liquid. It's important actually to note here when you think about this, one of the ways to know the exact temperature of a particular system, um, other than having a thermometer, but if you're wanting to validate your thermometer, one of the ways to know the temperature of your system is if you have a well-mixed system of two states of matter, then you have to be either at that melting point or that boiling point. A well-mixed container of ice and water is at 0 degrees Celsius. Any heat gained by that system would have to melt any of the ice into liquid before it could raise the temperature. Any heat lost from that system would result in liquid water being converted to solid before you could change the temperature. So a well-mixed system of any two states of matter is at that specific phase change temperature. When we talked about temperature changes, we talked about the specific heat, which is essentially the heating rate of pure substances. When we talk about phase changes, we're going to talk about the heat of phase change. So an example of that would be the heat of fusion, delta HFUS, is the amount of heat required to melt 1 unit mass of a pure substance. The heat of fusion is not, we don't properly measure that in terms of a final and initial. It just means the change in the energy of a system when we say delta H. We could look at the heat of vaporization, which is the amount of heat required to vaporize 1 unit mass of a pure substance, again in joules per gram. And then also notice there, the units for the delta H values do not have a temperature function in them because all phase changes happen at a constant temperature. So temperature is not part of that calculation. And then you can think about your other phase changes. So we'd have a heat of condensation, which is the amount of heat lost when a gram of a substance goes from a vapor to a liquid. Heat of solidification, heat of sublimation, heat of deposition. And again, that delta H, we call this the heat of, but that H does not stand for energy. It stands for enthalpy, which is just a measure of the thermodynamic energy in a system. Here are some delta H values. And one of the interesting things to look at here, if you pay close attention to this diagram, particularly the first column and the third column, because those are both in kilojoules per kilograms. And if you look at the heat of fusion, melting something, versus the heat of vaporization, vaporizing something, a significantly higher amount of energy is required to convert something from liquid to steam than from solid to liquid. And you'll actually hear within the context of firefighting, you'll hear it, the science of firefighting referring to the rate of steam conversion. So if you have some kind of a structure fire, you're dumping a bunch of water on it. What you're trying to do is you're trying to maximize the rate at which that fire is converting liquid water to steam, because that means that heat is not going back into the fire. It's being absorbed by that water, and removing that heat is one of the ways to put out the fire. Let's focus now on just the water, because we're going to do a few sample problems with respect to phase changes talking about water. I want you to notice something about this chart that's a little bit different. That we have it in calories per grams like we had the last one, but our kilojoules are not kilojoules per kilogram, they're kilojoules per mole, which a fairly simple conversion if you have a molar mass. So any heat of vaporization is just how much heat per amount of stuff. And so moles is a way to measure that amount of stuff. Also, if you know the heat of if you know the heat of vaporization, you also know the heat of condensation. Heat of condensation is just going to be the negative heat of vaporization. So system has to absorb energy to vaporize. It has to lose energy to condense back to a liquid. So it absorbs 40.7 kilojoules per mole to vaporize. It will lose that same amount of energy per mole to condense back into a liquid. And so if you know one of those values, you know the other. It just is the negative. Moving up and to the right on the curve is endothermic, positive processes. Moving down and to the left is exothermic, and those are going to be negative heat processes. Also, if you're given your delta H's in kilojoules per mole, again, if you want to convert those to the other units that we had, kilojoules per kilogram, all you need to do is divide by the molar mass. So you might take a second here. You might find the molar mass for water and divide that 6.01 by the molar mass. Now that's going to give you kilojoules per gram, because remember it's grams per mole. Then you're going to have to multiply it by 1,000 to get it to kilograms. And so when you do that, you should end up with roughly the 334 kilojoules per kilograms, which is what we saw for the heat of vaporization of water on the last table. Sorry, the heat of fusion. Also, sometimes you're going to be given your quantities in grams, and so it's useful to know that anything in kilojoules per kilograms is the same number in joules per grams, because you're just getting rid of the kilo on top and on the bottom. So the equation for a temperature change is Q equals mCp delta T. For a phase change, our Q is equal to the mass of the substance times the delta H. Again, there's no delta T in here because we have no change in temperature during a phase change. So how many joules are required to completely vaporize 55.0 kilograms of water, originally 100 degrees Celsius? So the first thing you want to do is you want to think about whether or not you're dealing with a phase change or a temperature change. And in this case, we are at the boiling point, and so we're moving across that DE line. There's no temperature change involved, so it's just Q equals M delta H. And so you're going to set your equation up, Q equals M delta H. M is 55.0 kilograms, and then you'll find that 2,260 kilojoules per kilogram for the heat of vaporization. You multiply your numbers together, and you're going to get 1.24 times 10 to the 5th kilojoules. Be really careful with these problems because the problem says how many joules. In a previous video, I did not make that conversion, and I should have at the end of the problem. But here, you need to make sure you get that into joules. You can set up the game board. 1,000 joules is equal to a kilojoule. So you're going to multiply that by 1,000 to get to your final answer, 1.24 times 10 to the 8th joules. So pretty straightforward process there. It's really important that this tells you, even though we're not putting any temperatures into the equation, that this is at 100 degrees Celsius. Because if we were looking at a different scenario, where, for instance, it asks you how much heat in joules is required to completely vaporize 1,500 milliliters of water, originally at 66.0 degrees Celsius, now we have a different problem. If you look at this one, we're starting somewhere on that CD line, maybe slightly above halfway at 66 degrees Celsius between 0 and 100. And then when we're done, we want to completely vaporize, which means we want to move all the way over to E. And so you're touching two different parts on the curve, which means you have two separate calculations. So we need a temperature calculation, mCp delta T, and we need a heat of phase change calculation, M delta H of vaporization. So you might take a second here, pause the video, set up your equation, see if you can calculate an answer here. Be sure to pay close attention to your sig digs, and when you come back, we'll work through the problem. So the first problem you might have run into here is that you need a mass of water and you're given a volume. Talked about this a little bit on one of the previous videos. Density of water is pretty darn close to 1 gram per milliliter. So if you've got 1,500 milliliters of water, you have 1,500 grams. Times the CP of liquid water, 4.186 joules over grams degrees Celsius, times the temperature change, 34 degrees Celsius. The temperature change there, right, is from final temperature, which is 100 degrees, and the initial temperature, which is 66 degrees Celsius. So 100 minus 66 gives us 34.0. Plus M delta H, 1,500, times 2,260 joules per gram. Let's think about units here. In your first part of the calculation, grams are going to cancel, degrees Celsius is going to cancel, and you're going to end up with 213,485 joules. Notice I've underlined that third significant digit, but I haven't rounded off yet. I only get 3 sig digs in my answer, so that's in the thousands place. And when I do my second calculation, I get 4 significant digits, but again, rounded to the thousands place. And so your final answer will have to be rounded to the thousands place. In that second part of the calculation, grams times joules per gram, the grams cancel, leaving you with joules. This is really, really important because you'll remember you can only add two numbers that have the same units. So notice our calculation here spits out the same units. We multiply those two numbers, or add those two numbers together, round them off to the thousands place. We're going to end up with 3.60 times 10 to the 6th joules for our amount of heat for that process. What if I'd wanted that in calories? Well, we know the conversion from joules to calories. 1 calorie is equal to 4.186 joules. So set yourself up a game board. Put your given piece of information in the top left. You think the calories go on top or on bottom. Hopefully you sorted out 4.186 joules goes on the bottom and 1 calorie goes on the top. We'll multiply across the top, divide across the bottom. And for calories, we should always expect a smaller number for calories. We're going to end up with 8.60 times 10 to the 5th calories. And so going back to the heating curve, so general process here, right? Positive slopes, those 3 different segments, you're going to use Q equals MCP delta T. 0 slopes, the flat parts on the curve, you're going to equal, Q is going to equal M delta H. Anything going up the curve is positive, anything going down the curve is negative. And then if you touch more than one part on the curve, you need to do multiple calculations. By the way, if you start at A and go all the way to F, that would have to be 5 separate calculations. You can't do one calculation for temperature change and one for phase change. The delta H on the 2 phase changes are different. The CPs are different for every different form, solid, liquid, and gas, of any pure substance. So the number of different parts of that curve that you touch is the number of calculations you have to add together.